Like Edward Teller, quite a big name.
Right.
In 1959, he actually proposed thorium to a U.S. oil company, pitched it as clean, non-explosive, and answer to CO2 concerns even back then.
Wow, 1959.
And he stressed how it was available pretty much everywhere globally.
And it wasn't just talk, right? They actually built things, kicked the tires on the technology.
They did, quite significantly, actually. The U.S. Navy, or rather a U.S. cargo ship, ran on thorium power for a whole decade.
A whole decade.
Yep, 62 to 72. And apparently without any major safety problems reported.
That's pretty impressive.
And around the same time, 65 to 69, they had a thorium reactor running on shore, too, at Oak Ridge National Lab.
So they had working examples, proof of concept.
Mhm.
What happened? Why did the U.S. move away from it if it was showing promise?
Well, the big shift seems to be around 1972. Admiral Rickover, who was hugely influential in the U.S. nuclear program, especially the Navy,
Go.
he, along with the Nixon administration, made a very strategic choice to double down on plutonium-based reactors, specifically the light water reactor technology.
And that effectively put the brakes on large-scale thorium development in the U.S.
Pretty much, yeah. It really locked down major thorium research funding and focus for, well, decades.
Yeah.
Really until about 2011.
Okay, 2011. What changed then? Why the flicker of renewed interest?
A couple of things, probably. Fukushima happened in March 2011. That obviously sent shockwaves through the nuclear industry, raising huge safety questions about existing reactor designs.
Right, that makes sense.
Well, some of the U.S. intellectual property, the research data from places like Oak Ridge, started getting opened up, made available to universities, other governments.
And that's the moment China steps in more forcefully. They weren't completely new to this, though.
No, not at all. China knew about thorium. They'd been aware of and likely tracking Canadian and French thorium projects from the mid-20th century. They had some background knowledge.
So when the U.S. research became more accessible, China was ready. They saw the opening.
They absolutely seized the opportunity. They had the context, they saw the potential, and they were positioned to really accelerate their own efforts.
Okay, so that history sets the stage. Early U.S. interest and even success, then a pivot away, creating an opening that China eventually moved into.
Uranium leads to plutonium-239. That's what you need for bombs. Thorium. You just can't easily make weapons out of it.
So in the Cold War context, uranium was the strategic choice, almost inevitably.
It really dictated the path of billions in research and development funds, yeah. Military applications drove the train.
Okay, but what about more recently, decades after the Cold War? Why didn't Western nations, like the U.S. or in Europe, reinvest more heavily in thorium as a power source?
That's more complex.
Yeah.
You could argue that in the U.S., for instance, the focus shifted to more immediate energy plays.
Like what?
Like massively expanding LNG, liquefied natural gas, exports, especially aiming for the European market after, say, issues with Russian gas supplies.
So short-term market opportunities might have overshadowed long-term, more complex tech investments.
Possibly. It's a different investment horizon. Developing and deploying a whole new nuclear technology like thorium MSRs, that's a multi-decade commitment. LNG export terminals, while complex, might offer quicker returns.
And that points to maybe a difference in strategic thinking, or perhaps just how Western economies and political cycles often work.
You could definitely make that argument. You know, the focus might lean towards shorter investment cycles, results within an election cycle, perhaps. Contrast that with China.
Right, what's the difference there?
Well, China appears to operate with a much longer view, certainly on strategic projects like energy. We're talking a 20, 30-year vision for thorium.
And they're backing it up.
Oh, yeah. With serious money, billions of dollars, and significant human capital, hundreds, maybe thousands, of scientists and engineers dedicated specifically to their thorium program.
So it wasn't just a lack of specific thorium funding in the West, maybe also a broader lack of a decisive strategy for next-gen nuclear.
I think that's fair to say. There seems to have been more policy hesitation, maybe a lack of a unified long-term vision for what comes after current reactor technology. Thorium was one option, but there wasn't that single-minded, state-backed push you see in China.
Okay, let's flip that then. Why did China go all in on thorium? What was their strategic calculation?
Primarily, it seems to be about long-term energy security, independence.
How so?
Their own estimates suggest they have vast domestic thorium reserves, places like the Bonobo mine in Inner Mongolia. The potential is enormous.
Enough to power China for.
I mean, some estimates are wild, talking tens of thousands of years. Even if that's optimistic, it represents a level of energy independence that uranium, which they largely import, or finite fossil fuels simply can't offer.
That's
2 bits of thorium wire. Now you can see the first problem with thorium is that it's radioactive, so you can't post it. There's no danger bringing it in my pocket because it's got a very thick piece of plastic, and thorium gives out relatively weak radioactivity, so there is no radioactivity outside this. Thorium as an element is not very widely used. It used to be used for the elements in gas fires. To get a good fire, you have some sort of ceramic element which gets hot and radiates the heat, because flames don't radiate heat very much. And thorium oxide is very stable, so people use ceramics based on thorium oxide. But the reason that people get excited about thorium is because of nuclear reactors. Nuclear reactors that are most widely used in the world are based on uranium. You remember that different radioactive elements can have so-called isotopes. These are chemically identical atoms, but which have different numbers of neutrons. And the uranium isotope, which is used in nuclear reactors, is uranium-235, which, when it is hit by neutrons, can split, giving out more neutrons, and you get a chain reaction. In a nuclear reactor, you want the reaction to go nice and slowly to keep the thing hot, so you can turn water into steam and generate electricity.
Thus we obtain a constantly increasing number of fissions called a chain reaction.
If you're building an atom bomb, a nuclear weapon, you want all your uranium to go bang at the same moment. The problem with current nuclear technology is, first of all, that potentially there's a shortage of uranium. It's a very rare element. Equally important, you can use the uranium in the reactor. The uranium-238, which is the isotope that doesn't take part in the reaction, can be used to absorb neutrons and make plutonium, which can then be used for nuclear weapons. So if you build a reactor somewhere, there is a danger that the waste products from that reactor, or some of the waste products, could be used for making nuclear bombs.
The atoms of the metals uranium and plutonium can be most readily fissioned to cause nuclear explosion.
And everybody in the world generally agrees that we have to try and reduce the number of bombs rather than making it easier for people to make more bombs. Thorium can be used for a completely different approach to nuclear reactors, but which still involves uranium. The most abundant isotope of thorium is thorium-232. If this isotope absorbs a neutron, it becomes thorium-233. Its mass goes up by 1. Then, sequentially, 2 of the neutrons split into a proton and an electron, and so it jumps from thorium to protactinium to uranium. So you generate uranium-233. Uranium-233 is a very rare isotope of uranium, but you can breed it from the thorium, which you've got a lot of, and the uranium-233 can then do your nuclear reaction, break apart, give you energy, just like the other uranium isotopes. But the difference is that it can't produce plutonium, and therefore it cannot be used to make bombs. Of course, you can say, well, if it splits in the nuclear reactor, why can't you make a bomb out of uranium-233? And the answer is, in principle you could, but as a byproduct of all the nuclear processes, you also get uranium-232, and uranium-232 is a showstopper. It absorbs neutrons and stops uranium exploding like a bomb. So it's safe in that way. The other advantage of thorium is that it's more abundant in the Earth, and because thorium-232 is the principal isotope compared to uranium-235, which is in only a small amount, There is an awful lot more thorium that could be used in reactors in the world than there is uranium.
Except you use a nuclear reactor to produce phenomenal quantities of heat.
The disadvantage is that you need to have some neutrons to get the thing started. You have to have a nuclear reaction to produce neutrons so that your thorium will turn into uranium. But that also can be quite an advantage because, for example, you can put waste plutonium mixed with the thorium and you burn up the plutonium and you get more fuel. It's a breeding reactor. The stability of thorium oxide, the one that was exploited years ago in gas fires, is both an advantage and a disadvantage. It's an advantage because your fuel is very stable. The downside of thorium dioxide being so stable is that you have to heat it to a very high temperature to process it. And that's not easy. Relatively little work has been done on thorium reactors compared to the now 70 years or more, nearly 80 years of research that have been done on uranium plutonium reactors. And therefore, the engineering, the safety, and so on is not developed to the same level, and the costs of building full-size thorium reactors would be very considerable.
It sounds like if all things being equal and we could start again, you would advocate going down the thorium route, and we're only doing uranium plutonium route because we've been doing it for so long.
Well, you have to remember that uranium plutonium route started because of the Manhattan Project, the atomic bomb project. I suspect that if nuclear power had been just started for civilian use, that the cost would have been prohibitive and people might never have used nuclear power. So it is built on the legacy of the weapons programs in many of the major countries in the world. We now have the situation where we understand how to handle radioactive compounds. We don't understand entirely how to deal with the waste in practical terms, though we do in principle. So it would be much more feasible now to go on the thorium cycle than it would have been in the 1940s.
That is the push for cleaner, safer energy. Thorium, especially in the molten salt reactor designs they're pursuing, has inherent safety advantages.
And it doesn't produce weapons-grade plutonium as a byproduct.
Right. Exactly. That avoids some of the proliferation concerns and aligns with goals for cleaner energy, less problematic waste. It fits a long-term sustainability picture.
So thorium is fertile, not fissile. It needs that neutron absorption step first.
Precisely. It breeds its own fuel, in a sense.
And the reactor type everyone talks about for thorium is the molten salt reactor, the MSR.
Yeah.
Why are they such a good match?
MSRs offer some really key advantages for using thorium and just generally. The big difference is the fuel isn't solid rods like in conventional reactors.
Right.
The fuel, the thorium, and the resulting uranium-233 is dissolved directly into a carrier fluid, which is a molten salt mixture. And that same molten salt mixture also acts as the coolant.
So fuel and coolant are one and the same liquid.
Essentially, yes. This immediately eliminates the need for the very high pressures you have in traditional water-cooled reactors. That's a major safety plus right there.
Less pressure, less risk of certain types of accidents. What else?
Well, the salts themselves have incredibly high boiling points. We're talking over 1,400 degrees Celsius.
Much hotter than water.
Way hotter, which means you physically can't have a steam explosion, a major concern in water-cooled reactor accidents. The system operates far below the boiling point of the salt.
Okay, that sounds inherently safer.
And there's another built-in safety feature people talk about a lot, the freeze plug.
The freeze plug. What's that?
It's basically a section of pipe at the bottom of the reactor vessel, kept cool, so a plug of the salt mixture stays frozen solid during normal operation.
Okay.
But if the reactor loses power or overheats significantly, the cooling to that plug stops. The frozen salt melts.
Okay.
And the entire liquid fuel salt mixture passively drains, just by gravity, into passively cooled dump tanks located underneath the reactor.
So it drains itself and shuts down automatically if things go wrong. No operator action needed.
Exactly. The nuclear reaction stops because the geometry changes and the neutrons escape. It's what's called passive or inherent safety.
That's pretty elegant, actually. What about efficiency, generating electricity?
MSRs, because they can operate at much higher temperatures than water-cooled reactors, have the potential for significantly better thermal efficiency.
Meaning more electricity for the same amount of heat produced?
That's the idea, maybe getting up towards 45% efficiency compared to the 30–33% typical for current light water reactors. That's a substantial improvement.
And you hear talk about MSRs and nuclear waste. Can they help with the existing waste problem?
That's one of the really exciting possibilities because the fuel is liquid. You can theoretically process it continuously or semi-continuously.
How does that help with waste?
Well, you can remove the fission products, the actual ash, from the nuclear reaction as you go. And some MSR designs, particularly burner reactors, could potentially be fueled with existing nuclear waste from old reactors or with spent uranium fuel. They could actually consume some of the nastiest long-lived isotopes.
So turning a liability into a fuel source.
That's the long-term hope for certain designs, yes.
Oh.
Plus, the ability to refuel and remove waste online without shutting down the reactor completely improves overall efficiency and economics.
Okay, so potentially burning old waste. What about the waste from the thorium cycle itself? Is it better?
Yes, significantly. When you run thorium through an MSR, the amount of long-lived radioactive waste, the stuff that stays dangerous for tens or hundreds of thousands of years, is drastically reduced.
By how much?
The numbers often quoted are up to 1,000 times less long-lived waste compared to traditional uranium reactors operating once through. Waste that is produced decays to background radiation levels much faster, potentially in around 500 years instead of tens of thousands. Still a long time, but a much more manageable timescale for geological disposal. Right, thorium is estimated to be about 3 to 4 times more abundant in the Earth's crust than uranium, and it's more spread out geographically.
So not concentrated in just a few countries.
No. Places like India, Australia, Turkey, Norway, the US, Brazil, they all have significant deposits. It reduces the geopolitical scarcity issues associated with uranium.
And the last big benefit often mentioned is proliferation resistance. Less risk of spreading nuclear weapons.
Yes.
Okay, let's recap the advantages then. We've got enhanced safety from low pressure and passive features like the freeze plug, dramatically reduced long-lived waste, higher potential efficiency, much greater fuel abundance spread globally, stronger proliferation resistance, the potential to burn existing nuclear waste. And some designs don't even need water for cooling.
That's another point, yes. Because the salts melt at high temperatures and cool efficiently, you don't necessarily need large bodies of water like traditional reactors do. You could potentially site them in arid regions, deserts even.
That's a compelling list. It sounds almost too good to be true. So what are the catches? The disadvantages or the big challenges?
Well, nothing's ever quite that simple, is it? There are definitely significant hurdles. One is just the sheer technological complexity.
Meaning?
Molten salt reactors, while the basic concepts aren't new, are still complex machines. Commercial designs are relatively young compared to the decades of operational experience with light water reactors. There's still a lot of engineering refinement and demonstration needed.
And you mentioned those high temperatures and molten salts. That must be tough on materials.
It's extremely tough. That's probably one of the biggest technical challenges right now. Molten fluoride salts, especially at 600, 700 degrees Celsius or higher, are very corrosive.
So they eat away at the pipes, the reactor vessel?
Potentially, yes. Finding affordable alloys and materials that can withstand that corrosive environment reliably for decades, the planned lifetime of a power plant is crucial and requires ongoing research and testing. That's a major material science problem. Right. China definitely has the most advanced operational hardware right now. Their TMSR LF1, that's a thorium molten salt reactor, liquid fuel one, out in the Gobi Desert.
The experimental one.
Yes. It achieved criticality, a sustained nuclear chain reaction, back in October 2023. That was a huge milestone.
And they've done more since then.
Yeah, by October 2024, they reported achieving online refueling while the reactor was still operating. That's a really significant capability for MSRs, something that was often discussed theoretically, but demonstrating it is a big step. Many thought that was much further off.
What's the power level of that reactor?
It's small, an experimental unit, just 2 megawatts thermal power. It's about testing the systems, the materials, the operations.
But they have bigger plans.
Oh, yeah. The roadmap includes a larger commercial-scale demonstration reactor, maybe 373 megawatts thermal, potentially operational by 2029 or shortly after. And then looking further out towards 2040, they envision deploying fleets of smaller modular MSRs, perhaps around 100 megawatts electric each.
So a clear stage plan for scaling up. What about other countries? Is anyone else seriously in the game?
There's definitely renewed interest globally. India has a long-standing thorium program driven by their large domestic thorium reserves, though their focus has often been on solid fuel thorium cycles.
Okay.
Russia is also exploring molten salt technology. In the US, you have private companies like TerraPower, backed by Bill Gates, developing MSRs, although their main initial focus seems to be a uranium-fueled MSR, not thorium, but the tech is related.
And Europe.
There are initiatives there too. Groups like NERIA and the Ryzen project are working on MSR concepts, often with a focus on modularity and potentially using thorium or burning waste. So there's activity, but perhaps less centralized and state-driven than in China right now.
And you mentioned applications beyond just grid power. Ships.
Yes, both sides are looking at that. China is explicitly exploring thorium MSRs for powering large container ships, aiming for zero-carbon maritime transport.
And in the West.
There's interest too. A company called Core Power, based in the UK, is working with consortia to develop marine molten salt reactors, looking at both uranium and thorium options for shipping. So maritime is definitely seen as a potential early market.
Okay, stepping back, what are the bigger geopolitical implications if China really cracks this technology commercially?
Well, it could be transformative. If China becomes the world leader in deploying safe, affordable, clean thorium power, it gives them enormous leverage.
How so?
They could dominate a next-generation energy market. They could offer energy independence or cleaner power to Belt and Road partners, strengthening those alliances. It potentially shifts the global energy balance away from fossil fuels and perhaps even away from traditional nuclear.
Last area, we hear so much about the massive energy needs of AI and data centers. Could thorium be part of that picture?
Absolutely. The projected energy demands for AI training and operation, and for the ever-growing number of data centers, are staggering. Finding clean, reliable, and dense power sources is becoming critical.
And thorium MSRs fit that bill.
Potentially, yes. Their ability to provide consistent baseload power with a small footprint and potentially sited closer to demand centers without needing massive water sources makes them a very attractive theoretical option for powering that digital infrastructure reliably and cleanly. It's definitely something people are starting to connect.
Okay, so as we wrap up this deep dive, what's the core takeaway for listeners thinking about thorium?
I think the key thing is recognizing that thorium, especially in molten salt reactors, represents a genuine paradigm shift possibility for nuclear energy. It's not just an incremental improvement, it's a fundamentally different approach with the potential for major advantages in safety, waste, and fuel availability.
And China's progress is really bringing this back into the spotlight after decades on the sidelines.
Exactly. Their advancements have made this technology feel much more tangible and near-term than it did even 5 or 10 years ago. It marks a really pivotal moment for a technology that was explored long ago, but never fully pursued by the West.
So, maybe a final thought to leave everyone with. We're seeing China push ahead strongly. Will the rest of the world follow suit and embrace thorium? Or will we see different paths emerge in this next generation energy race?